Hello, my name is Henry Zelenak, and I'm a senior at the State University of New York at Fredonia in the sound recording technology major with a minor in computer science. This research was done with the assistance of Dr. Shahin Medipour Atai in the computer science department. Our research focuses on identifying periodic signal patterns in audio streams. The presentation will go as follows. An introduction, followed by some preliminaries, are the main section talking about our actual research, samples and results that we tested, related works, conclusion and future work, our references for your perusal, and questions at the end. My email will be listed on the final slide, and it is also at the header of our paper, so you may submit questions to me via that email, and I will respond to them as promptly as I possibly can. So, a lot of audio signals contain periodic patterns, particularly those generated by sensor networks, or pedometers, different types of sensors. We wanted to find a lightweight method for identifying these periodic patterns in an audio signal, one that didn't necessarily use a Fourier transform or any of these other traditional, audio analysis methods. We've developed an algorithm which uses a similarity function and a similarity matrix, both of which have been used somewhat in the literature. And we used the programming language Python to implement this so that we can go in and make changes as we need. It also makes the ability to read audio files and audio streams much easier using this particular language. So the audio file or stream must be uncompressed. It cannot be a lossy compression format, as most sources will be uncompressed already. Without any additional processing, we would be using an uncompressed format. The pattern that occurs is a repetitive pattern in the signal against background noise. It should be of a relatively significant level above the noise so that we can detect it. It shouldn't be completely buried in the noise. It can occur at any frequency. Our algorithm does not discriminate against frequencies. It is based on sample and phase alone. Sample amplitude, I should say. Similarity function compares samples and phase slope, like I said, between samples, and each sample holds a discrete amplitude value. So these are the definitions of the periodic and almost periodic functions. Here in the top we have a periodic function, where tau is the period. Down here we have the almost periodic function with this error epsilon. And then down here we have the specifications of the similarity function. It must follow these rules. Example compare with itself will be the maximum value. It is symmetrical, fi fj equals fj fi, and it is a range that is within the range of the data, essentially. So, similarity matrix has the purpose of revealing periodicity in the audio signal. This is important. It stores, essentially, all of the outputs of the similarity function for each pair of samples. Color map, the similarity map is a color map that receives the matrix and displays the similarities visually. Alright, so these are the steps. First, we have an audio stream or file written to an array of integers in Python. The granularity is set using a slicing operator, and then we normalize the values from 0 to 1 as the range of the data is 2 to the n, where n is bit depth, so it can get very large for a large bit depth. For 16 bits, it's 65,536. So then we have the first derivative of the sample computed by finding the difference between the values of the previous and next sample. We'll see that in a later slide. And then within the similarity function, the first derivatives and the sample amplitudes are compared. So we're comparing amplitudes and phase at the same time. The similarity matrix is created and it is filled up with the output of the similarity function, and then we have the similarity map that's constructed from that. So this is the actual equation that we use. As we can see here, we have on the top 1 minus the absolute value of the sample amplitude at position I minus sample amplitude at position j. If it equates to 0, we get 1 minus 0, which is 1. And then similarly on the bottom, we have a constant raised to the absolute value of the phase difference, the phase first derivative difference. So that if that becomes 0, then we have a 1, and it's 1 over 1. That is the maximum similarity. So here is the graphic that describes how the phase is computed. It's essentially the first derivative at a sample is computed as the slope of the line passing through the previous sample and the next sample. So it's a slope. So here's some of our samples. We have a sine wave with a amplitude of 1 and a frequency of 1/6 hertz. As it goes in, you can see appearing across, as you traverse across horizontally, you can see 3 dark spots and 3 light spots in sequence. That is relating to the 3 periods that you can see here. The next one is a saw wave that's been pulsed. So it's got periods of silence in between, as you can see by the white squares. And then the actual sounds themselves are kind of represented by these spots in between. Here we can see another kind of a periodic signal, which is a siren. This has 7 envelopes, and you can see that there are 7 patterns here, and then there's a little white line running across the main axis. That is the perfect 1 values. Here's an alarm clock, and this is even better. We have a nice 4 beeps and followed by silence. As you can see, 4 beeps followed by silence. Works great. All right, so a few selection of the related works. Identifying periodical activities independent of video content. This is where the idea for comparing frames of a video file together comes from. It's similar to how we compare samples. Similar idea. It also uses a similarity function and similarity matrix. Here we have a spectral analysis. So we use estimation of period length using correlation methods, and then use an FFT to calculate the Fourier coefficients. So this is a more traditional type of method using a Fourier transform. Then we have a slightly different one using a discrete wavelet transform, which is significantly less computationally complex than this one here with the Fourier transform, but it's still a little bit more complicated than our method. Ours is very straightforward, and it doesn't use any frequency or spectral analysis like these two here do. So this third one down here has been applied to beat detection and complex musical examples. That certainly indicates to us that we could have used a discrete wavelet transform to identify periodic patterns in audio using the same type of method as beat detection is essentially that, identifying periodic patterns in an audio signal. So, in conclusion, we have developed a novel method for identifying periodic patterns using our own algorithm, and we have great accuracy with our results. We can use this to affect a certain type of compression, conceptual compression, which is based on the content of the signal. So we can have a very significant reduction in file sizes by taking the first instance of the periodic pattern and deleting the rest of them and appending instructions to repeat that first example so many number of times as it was in the original signal. This can result in huge reduction in file size. That would be a future work that we might pursue. Here's the references, which you can peruse on your own time, also in the paper. And any questions, you can email them right here to hzelenak@fredonia.edu. The email is also listed in the paper, in the header of the paper. Thank you for your interest and your time. It was a pleasure to present to you, and I hope you find this work as intriguing and exciting as I do. Thank you.